Force a standard large language model to play a long adversarial game of chess, and the illusion of reasoning quickly disintegrates. Chess requires strict, continuous state tracking over long horizons, an environment where traditional architecture reliably breaks down. The industry standard solution is to expand the system's nominal context, allowing it to ingest millions of tokens. But raw ingestion capacity is irrelevant when a task requires tracking rigid, rule-based state changes over time. Relying on semantic similarity for retrieval triggers state collapse. The system searches for concepts that look like the current board, which inevitably pulls structurally incorrect information from past turns. A common failure mode occurs when the model recalls a stale position from turn 40. Believing an old coordinate is still active, the system hallucinates an illegal move, teleporting a knight across the board. Pumping more tokens into the prompt window does not cure structural amnesia. Semantic similarity cannot substitute for rigid chronological dependency. The capped functional context harness addresses this through specialized chess and checker spaces running on a Cloudflare backend to test memory evaluation loops. In these environments, the system executes long-horizon adversarial games without illegal moves or positional hallucinations. This data table shows the biocapped V21 WASM-proof JSON benchmark scores compared to a traditional LLM baseline. The results show 1.0000 scores for both retrieval and provenance trace accuracy. The system maintains a 1.0000 score for staleness handling, indicating the continuous rejection of outdated board positions. This metric measures functional context, the system's ability to preserve exact chronology, dependency edges, and contradiction states under real task pressure. This performance is built on 3 pillars. The first is the provenance ledger, an append-only cryptographic record. The second is causal surprise minimization, or CSM, which restructures how the model plans its actions. The third is deterministic WebAssembly execution, which locks operations to a sealed environment. Eliminating cognitive drift requires abandoning probabilistic token prediction in favor of verifiable architectural determinism. To understand how this determinism is achieved, we have to look past the user interface of the chessboard and examine the raw data structures governing the pieces. This scatter plot represents a traditional vector database. It relies on floating clusters of semantic text mapped in an abstract space, without structural links. The capped evidence graph organizes these points into a rigid graph structure, connected by directed chronological lines indicating strict dependency. Nodes in this graph consist of exact source-packed claims, mapping board coordinates at specific moments in time. The edges connecting those nodes strictly encode the temporal order and causal dependency between those claims. Discarding similarity search in favor of a directed graph allows the system to map reality without semantic hallucination. Running alongside that evidence graph is the provenance ledger. This append-only record connects every output directly to the exact runtime facts and policy decisions that produced it. During a chess game, executing a move generates a new ledger entry tagged with a precise chronological timestamp. Because the timeline is enforced cryptographically, the creation of a new state actively invalidates the old memory of that piece's previous position. The system structurally rejects stale memory through the ledger, ensuring that contradictory old context cannot be recalled as a current fact. While the ledger and evidence graph handle how the system stores the past, a separate mechanism plans future actions. Standard autoregressive generation operates through stochastic guessing based on correlative probability, identifying which token most likely follows the last. The causal surprise minimization module replaces correlation with Judea Pearl's causal hierarchy. This diagram illustrates the application of interventional due calculus. It moves the system's logic from simple observation to actual causal planning. The system uses this mathematics to map out counterfactual what-if pathways, simulating the consequences of potential chess moves before executing them. It evaluates each branch and executes the pathway that minimizes causal prediction error at the interventional level. By replacing heuristic task ordering with structural causal planning, the system eliminates stochastic drift during decision-making. Even with an exact memory graph and a causal planner, The logic requires a stable physical substrate. If the underlying execution environment permits stochastic variance, even a perfect causal model will produce hallucinated outputs. This is why the architecture utilizes the capped WebAssembly backend, deployed on Cloudflare's rigid edge infrastructure. When the environment initializes, it ingests a versioned manifest file. Cryptographic verification of byte sizes and SHA-256 hashes must pass before any action is logged. This terminal readout displays the capped.context.prove.wasm.bundle protocol, which verifies local artifact hashes against the manifest. The protocol also audits specific metadata, requiring the zero imports and telemetry off flags to clear, sealing the binary from external interference. This cryptographic sealing prevents hardware-level stochastic variance, providing a stable anchor for the entire logic layer. By tracing data flow from the hardware hashes through the causal decision tree and finally to the move on the board, the hardware, logic, and memory layers lock together into one continuous state. The successful completion of a complex game proves that these three architectural pillars are fully integrated. This completion audit report summarizes the system's proven state across all 7 core requirements. The Provenance Ledger locks the history. Causal surprise minimization plans the future. WebAssembly provides the unalterable mathematical anchor. The architecture solves context degradation not by expanding storage for more tokens, but by updating a cryptographically secure state machine. These chess and checker spaces are rigorous public proofs of functional memory operating under continuous adversarial pressure. Sovereign, hallucination-free artificial intelligence requires highly structured causal execution environments. Expanding nominal context windows cannot solve the structural failures inherent in similarity-based retrieval. True cognitive architecture demands architectural determinism.